For this lab, we were tasked with recording an object moving at a constant velocity and to create a computational model to predict its position at any given time. I chose to record a tennis ball and attempted to have it move at a consistent speed in the same direction with no net force acting on the ball. However, rolling the ball for an extended period of time did not allow for it to remain at a constant velocity because I couldn't eliminate all the other forces acting on the ball. For example, the friction of the ground and resistance from the air were a few of these external forces. For this reason, I had to keep my video short and captured the ball moving at the closest thing to a constant velocity that I could achieve. This allowed for my computational model's data and my experimental data to only have slight discrepancies from one another. This lab addresses the relationship between forces and motion, and this is important to understand because it explains why everything around us behaves in a certain way, whether it's staying still or remaining in motion. Because of this, it's vital that we understand what exactly is making a ball, in this case, travel at a certain velocity and then stop after some time. The first fundamental principle that must be understood for this lab is velocity. Velocity is defined by a vector expression of the displacement that an object or a particle undergoes with respect to time. This definition is best understood in my opinion through velocity's formula, v equals delta r over delta t, where r is position in meters and t is time in seconds. The change of position and time are both calculated by subtracting the initial from the final, and velocity must also have both magnitude and direction. The next fundamental principle to understand is Newton's second law, which is best represented for this lab through the equation delta v over delta t equals F net over m, where delta v over delta t is acceleration, F net is the total force acting on an object, and m is the mass of that object. It's important to note that using this equation, we can determine that in order for the change in velocity to be zero and the object to remain at a constant velocity, the net force must also be zero, meaning either that no forces should be acting on the ball or that all the forces acting on it must balance each other out. It's also important to note that you can assume that mass could take on any value without affecting a constant velocity because both force and velocity would equal zero. This ties to the last fundamental principle, which is Newton's first law. This law further explains the object will only stay at a constant velocity or in motion so long as no force is affected, and this is known as inertia. So for this lab, I began by recording my tennis ball moving at what I thought was a constant velocity. After putting my video into Tracker, I found that the velocity changed during the video, so I shortened my video by a few seconds to find a clip where the ball was moving at a relatively constant velocity. I will play it now. Using Tracker allowed me to calculate this velocity very easily, and if I were to have flipped the axes, I would still get the same magnitude for my velocity, but would have to take direction into consideration, like in the case where it might be negative. I then began by creating my computational model through GlowScript. For the actual coding, some calculations were necessary to find my average velocity. I took the initial time in position and the final time in position and used my formula to find that my average velocity was 0.6785 meters per second. I then plugged this value into my code for my ball's velocity and changed my ball's position to the initial position from the video. The next thing to change was a formula to update the velocity, which is a manipulated version of Newton's second law. I then had to change the ball's position, which is a manipulated version of the velocity formula. The rest of the coding was very straightforward, and I will run what I got now. So you can see the ball moving, and then there's the graph and my data underneath of it. Now that I had both sets of data and I plugged this into a spreadsheet in order to see my results on a graph. There was a slight discrepancy between the blue dotted line, which represented my experiment position, and the red dotted line, which represented my predicted position. This is likely due to the fact that in a real-world setting, it's difficult to eliminate all forces acting on an object, and friction was keeping my tennis ball from traveling at a true constant velocity, like in my computational model. It's difficult to determine the many forces acting on an object at any given moment in a realistic setting. The best approach is to analyze the different interactions a system is having within the context of its known surroundings. This way, you can add all of the known forces to determine whether or not an object is really moving at a constant velocity. Overall, this lab taught me the relationship that velocity has with force and provided real-world examples of Newton's first and second laws. In future experiments, I would seek out a situation that did a better job at eliminating external forces. For example, a hockey puck sliding on ice might have less friction than a tennis ball on the ground, so this might provide a more constant velocity to be analyzed.